So, we've been talking about AC circuits since last Monday, because this is a Monday-Wednesday class. I will eventually get that through my head. Can't tomorrow be Friday? Okay. And one of the main things we have to deal with AC circuits is AC Ohm's law, which basically says V equals I times Z. And this Z thing is impedance in ohms. And it is like resistance, but for AC. We use a different symbol and a different name for it to remind us that it's not exactly like resistance. So we have three basic passive components in AC circuits, and each one has a different Z value. For a resistor, it's just Z is equal to the resistance. So we get to use Ohm's law with just the plain resistance in AC circuits. It works just fine. And for the inductor, Z is equal to 2 pi F L. So the thing that an inductor has that's pretty constant is the L value, the inductance itself, measured in henries. And depending on the frequency, the inductor will interact with an AC signal in different ways. If you have a very low frequency, the inductor will have a very low impedance because the impedance is proportional to F. And that means the inductor allows low frequencies to pass through. Whereas if you have a high frequency, the inductor reacts. So we call that quantity reactance sometimes by having a high impedance. And it basically blocks high frequencies from going through. And then the last one is the capacitor, where Z is the inverse, 1 over 2 pi F C. So for the capacitor, once you build it, the capacitance, the C value, is difficult to change. There are some capacitors that have a variable geometry. They can change shape. Often the way they change shape is by having metal fins that will overlap with each other and then move away from each other. And the amount of overlap is proportional to the capacitance. Interesting note, we all have cell phones that we carry around. Pretty much since the Nintendo Wii came out, the first Wii, we've had good electronic accelerometers. So a chip can know what direction it's pointing. The way these chips work is they basically have two combs, two sets of fins. One is locked in place, it's rigidly connected, and the other is on a long arm. And when you move around, the locked one moves first, and the one that's on the long arm has a little bit of a delay because it's hanging out in space. So when the fins overlap or unoverlap, it changes the capacitance, and then the microchip measures that. So that's how our phones know when you rotate the screen, whether you're in portrait or landscape mode. That's how the video game controllers know that you are turning it and moving things around. It's through capacitance. And they make these capacitors really, really, really small. So they're part of the microchip, and they're literally microscopic in size. Inductors, it's more difficult to make tiny inductors because you need to have a certain amount of magnetism to have an effective inductor. But little capacitors, yeah, we have lots of those. So this is all about the resistor, the capacitor, or the inductor, one at a time. So what we want to know is what happens when we combine these things in a circuit. And there are two types of circuits we could look at. We could look at series circuits or parallel circuits. As it turns out, the math is a lot easier for series circuits, and we're only going to do those. The parallel circuit math is a little bit more complicated, and we're gonna skip that. I'll mention one idea about the parallel circuit as we get toward the end of today, but that's about it. So our main idea about a series circuit is that everything in the series has the same current. And that's still true in AC, and that's fortunate. There's another idea we have about series circuits, and that is that voltages add. Now, there's an important distinction here, that V total is equal to V of the resistor times sine 2 pi ft plus V of the capacitor hang on, I'm going to get this right. Times minus cosine 2 pi ft plus V of the inductor times regular cosine 2 pi ft. Inductors and capacitors do a weird thing with the current and the voltage. And the weird thing they do is they'll take a current that looks like a sine function and turn it into a cosine function. Now the resistor will take a current that looks like a sine function and keep it as a sine function, and that's fine. So the resistor still has a sine function, but the other two have cosine functions. So that's a little weird. So this turns into V of the resistor times sine of 2 pi ft plus V of the inductor minus V of the capacitor times cosine of 2 pi ft. So let me skip to a result. And that is that actually, I'm not going to call it that. That's the result I want to skip to. So the way these sines and cosines add up is kind of like a Pythagorean theorem. In fact, there's an analog for these voltage values, which are sines and cosines, that kind of turns them into vectors with x and y components. And that's, in a sense, what we've done here, is we've taken the sine one and thought of that as like an x component, and taken the cosine one and thought of it as a y component. And when you have a vector that's split into x and y components, you have to do the Pythagorean theorem to find the magnitude. And that's exactly what that statement is a Pythagorean theorem for all of these voltages. So there's kind of a statement I can make about it that summarizes what we've just done. Did I not spell Pythagorean correctly? Oh, because it's a guy, I'm supposed to capitalize it. Oops. So two of the weird things that happen here are that the capacitor and the inductor end up kind of canceling each other out. That's one of the weird things, because the capacitor ended up creating a negative cosine function and the inductor ended up creating a positive cosine function. And they're both still oscillations. They both still have independent magnitudes and independent RMS values. But when we add them up in a series circuit, they cancel each other out. So we have to subtract those first. And the next weird thing is the more obvious one, that there's a Pythagorean theorem going on here. So how do we adapt this into an impedance rule for the series circuit? Well, the impedances are going to add the same way. I don't know if you remember a long time ago, we did series resistors, and I said the voltages add in series resistors. And look, because the voltages add and Ohm's law works, it means the resistances add. The idea of resistances adding was because of the way the voltages add. And we have the same thing here. The way that the impedances combine is because of the way that the voltages combine. So the way we usually write this is as follows. Capital Z is the big square root of R squared plus X L minus XC parentheses squared. This looks just like the voltage formula, except I've translated each one into its corresponding impedance value. Now, how do we actually apply this? I usually don't apply it as a big giant formula like that. I usually split it into a few separate formulas. So I usually use Z squared equals R squared plus capital X squared. And capital X is XL minus XC. So I kind of separate the Pythagorean theorem step from the subtracting the capacitor and the inductor step. And in doing that, it makes it a little bit easier on me. It makes it less annoying to deal with. So now that I have all of these formulas laid out, is there kind of a graphical or a mnemonic way of thinking of this? There is. The graphical method is vector addition. So if I draw a set of axes here, this is the R direction, this is the X sub L direction, this is the X sub C direction. So for any given impedance, for any given series circuit, you might have a certain amount of resistance. So you go out that way a little bit. And then you might have some inductance. So you head up that way a little bit. And then you have some capacitance. So you head down that way a little bit. And this point here is Z total. And this dashed line, the length of that dashed line is the actual impedance that we're looking for, that we can either measure because we can measure current and voltage in a circuit, or that we're trying to calculate because we know what inductor, capacitor, and resistor went into the circuit. So we should do an example. We shouldn't just leave this at big general formulas. And I have an example prepared. But I want to make sure everybody's had a chance to write this stuff down. I'll write the general formulas down again as we use them on the next page. Sir.
So up there when you had the formulas, inductor Z is equal to 2 pi FL?
Yes.
So is that the formula to get the reactances, or is reactance?
It really is. This is called X sub L, and this one is called X sub C.
You wouldn't have to divide by 2 pi after that. That's part of the formula. Yeah.
Yeah, the X sub L is part of the is the impedance of an inductor, and that includes the 2 pi.
And that's the same thing as saying VLRS?
Well, the voltage is related to the Z in that they're proportional to each other. So the reason that I got to jump from a thought about voltages to a thought about impedances is because it's a series circuit and everything has the same current. So I kind of factored out the current, which turns voltage into impedance. So that's kind of the math of why we have this weird way of dealing with impedances in the series AC circuit. Now, once you accept that, oh, we have these formulas and we have to use them, then we should actually practice using them. So this is called a series RLC circuit. And we're going to put a voltage in series with a resistor. That's the R, and an inductor. That's the L, and a capacitor. And that is the C. And this is our EMF. So the symbol for the resistor is a little jagged squiggle in the middle of your wire that we've been using. The symbol for an inductor looks like a bunch of loops. And some people actually draw them as loops instead of, I don't know, instead of hitting the line with a point at each one. As long as it looks curly, at least on one side, it'll count as an inductor. And then the capacitor, we put a break in the wire and put the two parallel lines next to it. So what we're going to have here is that EMF is equal to 140 times the sine of 500 T. And we should compare this to a generic form, EMF max times the sine of 2 pi f t. So already we have a little bit of information we can extract out of this thing. We can say EMF max is equal to 140 volts. And that means that EMF RMS is 140 over root 2 equals 99 volts. Usually when I do Ohm's law calculations in AC, I like to use RMS values for everything. Now the other thing we can extract here is that 2 pi f is equal to 500. So therefore f is equal to 500 over 2 pi is equal to 79.6 hertz. So that frequency is a little bit faster than our standard AC in the United States, but it could be made with a signal generator. You use the signal generator in last week's lab to get lots of different frequencies. So there's information about one component. Now, let me give you your given information about another component. R is 1 kilo ohm. So that's R is 1,000 ohms. And right now, we can't really do anything with that because we don't know how much current is flowing. We don't know how much voltage the resistor itself is exposed to. All we know is the total voltage. So we kind of have to work at more of the circuit. So we're going to be given L is 1.0 henries. And then we're also going to be given C is equal to 1.0 microfarads. So let's figure out the X sub L value. So that's 2 pi FL, which is how much? That is a very good thought, that 2 pi f is 500. Because why bother using this value here, where we've divided out the 2 pi, and then just have to multiply it by 2 pi again for that formula? So then if we use 2 pi f is 500, and then multiply it by 1, we just get 500. So that's one of the tricks that can sometimes be used with AC circuits. And then we want to calculate the X sub C. That's 1 over 2 pi FC, which is 1 over 500 times 10 to the minus 6th. So the 500 is the 2 pi f, and the 10 to the minus 6 is a microfarad. And that comes out to 2,000 ohms. So we have this circuit where the way it's set up and the way it's operating, we have 1,000 ohms and 500 ohms and 2,000 ohms all in series, but they're not resistances, so we cannot add them. We have to combine them step by step. So we can get X is XL minus XC is technically negative 1,500 ohms. Yeah, it's technically negative.
That where the theory comes in, when it squares, that's good.
Yeah, we're going to square it. So it comes out negative, and one interpretation of that is that the capacitor is being stronger in this circuit, because the capacitor is the one that's getting subtracted in the overall reactance formula. And now we can calculate Z as the square root of R squared plus X squared is the square root of 500 squared plus 1500 squared equals 1803 ohms. Notice that when I'm squaring it in the Pythagorean theorem, I'm not going to put in the minus sign there, because if I did, I'd have to put in extra parentheses, and I'm lazy, so I don't want to do that. And the easiest way to deal with it is just not to use the implicit minus signs when you're using the Pythagorean theorem, the ones that are built into variables. So now we have an overall impedance for the circuit. This is the whole circuit. We have the whole circuit's voltage, we have the whole circuit's impedance, so we can calculate the whole circuit's current now using regular AC Ohm's law. So we can do V total is I times Z, and this was 99 volts is I times 1803 ohms. So I is equal to 0.0549 amperes. Remember, that is, maybe I should write it RMS. We used the RMS voltage, so we got out of it the RMS current as a result. So now that we know the current, we can go back and find out more about the resistor. We could do V equals I times R, which is 0.0549 amperes times 1,000 ohms, which is 54.9 volts. And we can do P equals V times I is 54.9 volts times 0.0549 amperes is 3.2 watts. And one of the things I have to point out is that this power that we calculated for the circuit, this is the only power that the circuit uses. The inductor doesn't use power, the capacitor doesn't use power, just the resistor. And it's not equal to the overall voltage times current. So V times I is 99 volts times 0.0549 amps. And that is a quantity which is 5.4 volt amperes. And this is one of those weird cases where scientists and engineers have chosen to be a little bit specific about the units when a certain kind of calculation is done. So if your calculation is for a resistor, then the voltage times the current is the power in watts. But if your voltage times current is for an overall circuit, technically it's not the power in amperes, it's called a volt-ampere rating. And sometimes we have industrial equipment that's rated for a certain number of volt-amperes, such as a battery backup for a computer system. Sometimes they're rated in volt-amperes. And that's generally because they're capable of generating a certain amount of current. And that's what they're really trying to get you to limit, is the amount of current you're using from that device. So to run an entire computer system for 5 minutes, which should be enough to save your files and shut down nicely, you probably want to have a battery backup that has like an 800 volt-ampere rating and 5 minutes of runtime. So we can answer some other questions about this circuit. We can find out what's the voltage across the inductor. So for that, we use V equals I times Z, where the current is just the current. It's 0.0549 amperes. But the Z value we use for finding the inductor voltage is just the inductor's Z value. It's just the 500 ohms. And I think I did not calculate that ahead of time. $27.5 volts. And then for the capacitor, V equals 0.0549 amps times 1500 ohms equals times 3, 82.4 volts. Now look at those three voltages. They do not add up to the overall EMF of the circuit, because the capacitor is already up at 80. If you just added the 20 more from the inductor, you'd already be past 99 volts. And then there's still 55 volts across the resistor. And that's because of this cancellation of voltages in AC circuits, that the inductor and the capacitor cancel each other out. Wait, the capacitor wasn't 1500, was it? The capacitor was 2000, wasn't it?
Yes.
Okay, so we got to fix this. 2000. So $109.8. It's worse than I thought. The capacitor's voltage by itself is more than the power supply's voltage. And that's real. It's actual. So if you put a voltmeter across the capacitor in this particular circuit, you would measure more voltage across the capacitor than your power supply generated in the first place. And that's one of the weird things that can happen in AC circuits. And it's because the capacitor doesn't generate voltage by kind of receiving voltage. The capacitor generates voltage from having charge accumulate in the capacitor. And it was actually the inductor in the circuit that was kind of getting some current flowing and then pushing extra current in the capacitor so the capacitor could generate this extra voltage. Now, we wouldn't necessarily be able to use this to change voltages like we do with transformers. So this is not like an efficient way of multiplying voltages. It's just kind of a side effect. But it's an interesting side effect. It is possible that a circuit like this could end up shocking a person. So you could have a circuit where there is only like 10 volts in power supply, but something like this could generate a large enough voltage that a person might get probably not killed with small equipment, but maybe feel discomfort. So it's one of the things to be careful about with radio equipment. Usually our radio equipment's inside of boxes, so we don't have to worry about this. So that's my series RLC example. There's a whole lot of different calculations that go in there. But at any given point in the calculation, I looked at what information I had, and I tried to find a small formula applicable to the AC circuit that would use the information I have to get me a little bit more and get me further down toward a final answer. Any questions on that example? Now, I promised somebody that I would answer a homework question. So I am going to go over here and pull up WebAssign. Can you tell me what question you're talking about?
That is like a very easy question.
That's fine.
I believe it was number 4.
Magnetic flux?
Yeah.
Okay. So this is homework 4-4, magnetic flux. So there's a couple of different formulas for magnetic flux. One of them is that for a loop, the magnetic flux, which is this capital I with a circle in the middle of it, is equal to B times A times cosine theta. For a coil is like N loops. So we just have to multiply an N on there. And then for a coil, usually we think about that cosine theta as being 1 because the magnetic field goes straight through the coil. The only time that's not true is when the coil is like a generator coil. And then there's one more. The inductor. The magnetic flux of an inductor is the inductance times the current. So we had taken these things and combined them together with B is mu naught times N times I over L to figure out that, not capital L here, this is curly L, the length of the coil, to figure out that L is mu naught N squared A over curly L. and those were specific to a solenoid. So those were a whole bunch of the formulas that we tossed around and got different answers to. Now, in this particular homework question, so in homework 4-4, we're told VRMS is 120 volts, and we're told F is 60 hertz. And we want to know flux max. So since flux is proportional to current with just a constant, it has the same idea of an RMS versus a maximum value, but we can calculate the max flux just by using the max current. So if only we could calculate the maximum current, then we could multiply by L and find the maximum amount of flux. So can we calculate the maximum current from an RMS voltage? How about VRMS is equal to IRMS times the impedance, which is what we just talked about today. So this says IRMS is equal to VRMS over 2 pi FL. So that impedance is 2 pi FL. So I plugged it in and divided it down to the other side of the fraction. Somebody is swatting flies or something on the other side of that wall. So how do we turn the RMS current into a maximum current? They're different by a factor of the square root of 2. The RMS is less by a factor of the square root of 2. So all we have to do is multiply by the square root of 2, and we get a maximum value. So take this fraction, put another square root of 2 on it to get the maximum current. And then here's the wacky part. Even though we don't know the L value, in order to calculate the flux, we're multiplying by L. That cancels the unknown L from this formula. So we can just kind of ignore the fact that we don't know L, because it cancels out anyway. And that is what makes it all fall together. The first time I saw this question, for about 30 seconds, I looked at it and I said, wait, they're not giving an inductor value. And I thought, okay, what I should do is charge ahead and just make the inductor value capital L, even though I don't know it, and see what happens. And by the time you get to the end, you're multiplying out an unknown L that you didn't know in the first place. So it doesn't matter what L is. So basically, any inductor that you plug into a wall outlet is going to have this same amount of flux, same amount of magnetic flux. So I thought that was an interesting question, which is why I left it there. Now, there's one more thing I want to talk about. That's the idea of resonance. So this comes about because X equals XL minus X sub C. And because that happens, they can cancel. But what does that have to do to us for our overall circuit? Z is the square root of r squared plus capital X squared, which is just the square root of r squared, is just plain r. And it's almost like the inductor and the capacitor aren't there. The overall impedance of the circuit, if the inductor and capacitor's reactances cancel, is as if you just had a resistor. So how can this happen? Well, we need X sub L equal to X sub C. If those two things are equal, then we achieve this special situation of resonance. And then the inductor and the capacitor cancel each other out. So this is 2 pi f L equals 1 over 2 pi f C. So the easiest thing to do here is to multiply the 2 pi f over to the other side and divide the L over to the other side. So I multiplied the 2 pi f over to the left. So now I have two factors of 2 pi f, so it's squared. And then I divided the L underneath the right-hand side. And then it's usually common to take the square root of both sides. So that is 2 pi f equals 1 over the square root of LC. Or f is equal to 1 over 2 pi times the square root of LC. And it's a special frequency for a given capacitor and inductor, and it's called the resonant frequency of those two things. So when you put them together in the circuit, they resonate and they make this happen. So let's figure out what's the resonant frequency for that previous example. So L was 1.0 henries and C was 1.0 microfarads. Those were the values from the previous example. So that means that I can calculate the frequency of resonance. It's common to put a little R on there, or a 0 for resonance, is 1 over 2 pi times the square root of 1.0 times 1 times 10 to the minus 6. So that gives us a resonant frequency of 159 hertz. Is that right? I haven't recalculated that value in like 3 years, so I don't know if it's right. Yeah, 159 hertz. So in the previous example, we were operating at 80 hertz. It was 79.6 hertz. But the resonant frequency is 160 hertz. So that means we were operating below resonance. And as the frequency goes down, the capacitor gets stronger and stronger and stronger and says, no, I don't want current to flow. The most extreme would be zero frequency, where the capacitor completely shuts down the current. But we were only a little bit low in frequency, so the capacitor was stronger at blocking the current. So what would happen if we operated at resonance with the same voltage? So then we would have I equals V over Z equals V over R. Is 99 over 1000 equals 0.099 amperes. And we end up with more current flow. And that's how radios tune to different signals. Our FM radio dial goes from like 90 to about 108 megahertz. And each station broadcasts at a particular frequency. Your radio has capacitors and inductors in it. And by changing the selected frequency, you're changing the selected resonant frequency of that inductor and capacitor. And then you're letting the current flow through for that particular frequency while blocking it from all the others. So we could make a graph here of I versus F. And my title of my graph is Constant Voltage for a Series RLC Circuit. And what it looks like is almost zero, and then there's kind of a hump, and then it's almost zero again. And this point right here, this is the resonant frequency. And depending on the relative strengths of the resistor and the inductor and the capacitor, that hump can be a really wide hump or it can be a really narrow hump. Well, what's always true is at this point here, that's the low frequency range where the capacitor blocks the current. And this point here is high frequencies. Where the inductor blocks the current instead. And it's that special frequency in the middle that is the resonant frequency where you actually get something happening. Now this phenomenon of resonant frequency and resonance doesn't just happen in RLC circuits. There's a lot of places where it happens. Imagine pushing a child on a swing. If you push the child 5 times per second, not much is going to happen. because you're going to push them and they're going to move up a little bit, and you're basically going to hold them up on one side of the swing. They won't have time to swing back before you push them the next time. If you push them at exactly the same frequency that they're swinging, then you can give them a boost, they can come back around, and you give them another boost, they can come back around, you can give them another boost. That is a similar relationship between a stimulus and a result that happens here. So this F here is the stimulating frequency. That's the frequency we have our power supply set to. And depending on whether we set our power supply, our signal generator, to the resonant frequency or a different frequency, the current is the result, the response of the circuit. In some ways, this is kind of how microwave ovens work, because microwave ovens have an oscillation. It's a radio wave that comes in, and there are springs inside of molecules that shake back and forth, and the frequency of the microwave radiation is tuned so that the springs will receive that and turn it into motion. And then once the molecules are all shaking around, that is effectively our food being hot. Now the parallel RLC circuit is similar, but the math is harder. And the net result is that the current graph is kind of inverted from the series RLC circuit. So if I draw a graph of I versus F, I kind of need a baseline here. So this is I equals V over R. And what the actual circuit does is it basically follows this baseline for a while and then drops down to 0 and comes back up and then follows the baseline. So at very low frequencies, the inductor allows the current to flow. And at very high frequencies, the capacitor allows the current to flow. So I should draw kind of what I'm thinking of as the circuit here. So there's my R, there's my L, there's my C, and there's my EMF, R, L, C. So this is low frequencies. The inductor allows current to flow, and this is high frequencies where the capacitor allows current to flow. And at that middle frequency, instead of either one being able to allow the current to flow, they kind of gang up on each other and block the current completely. So even though you might think, shouldn't current be able to get through the capacitor at a moderate frequency? Because the capacitor has a moderate impedance at moderate frequencies. And the inductor has a moderate impedance at moderate frequencies. So shouldn't they let the current flow? Because it's not like you're saying that the impedance is infinite of any one individual component. But when you combine them together in parallel, it turns out that it is. And that's the weird part of dealing with a parallel circuit. So in the series RLC circuit, the one I make you do calculations of. At resonance, the inductor and the capacitor basically cancel each other out, and the current flows through just the resistor. And in the parallel RLC circuit, it does that. That's something called a notch filter, because there's kind of a notch in the graph. Notch filter, yeah?
So you said the solid line, that's the actual, but the dotted line, that's what we would calculate? Or what's
The dashed line is the resistor only calculation.
Oh, okay.
So this is R only. And this is LC in parallel. So there's my key for what I drew. Yeah. So I was saying that's a shape called a notch filter. I don't know if you've ever had the experience of being at some gathering of people where they have to use a microphone and a speaker, and they turn the microphone on, and all you hear is, yeah. Well, if you have a professional soundboard, they can get rid of that sound by tuning a notch filter to that exact tone, and then they can turn the microphone up more, and the person can speak and get heard, but won't make that feedback sound. It has a side effect of getting rid of any singing at that particular frequency, but if the person is just speaking, not singing, it doesn't matter so much.
So if they were singing at that frequency, you just wouldn't hear it?
It'd be like there'd be missing notes. So they could sing like normal, and then they get down to that note and it just, yeah.
Like when you mess with the equalizer on your stereo.
It basically, yeah. This is like a very specific equalizer. Like if you had a 100-band equalizer and could turn down just one of the notches on it, one of the sliders. That's kind of what this does. Now the math of this, like I said, is harder. It's easier to do if you flip over from vectors into complex numbers, and then you're allowed to divide and do Ohm's law calculations in reverse with complex numbers, which you can't do with vectors. So without the vectors, or without the complex numbers, you basically have to know all of your trig identities, which I don't. I always did it with complex numbers. Okay, well, that's what I have for today. On Thursday, Wednesday, you ever get this thought stuck in your head and you just can't get rid of it? Yeah.
You also have other classes.
I do have a Tuesday, Thursday class. It's not okay.
Do you call them Monday, Wednesday?
No, I don't. I just call everybody Tuesday, Thursday. So on Wednesday, we're going to talk about transformers. Please feel free to bring homework questions also on Wednesday, and I will help you out anywhere you're stuck. And then on Monday, we will review. And next Wednesday, we have exam 2. I got it right every time. That's why I stop in the middle of my sentences, so I can think about the words I'm about to say. Yeah. Hang on.